Alright, so let me summarize this for you a little bit. Say we have more complicated functions, or even the linear functions we were talking about before. If you take this top function, polynomial, and it turns into 0, right? So I plug in an x value that makes the numerator equal to 0. What am I going to get on the graph? Pick some x value, and I've got a y value of 0. Oh, what is that? That's an x-intercept, right? So x-intercepts of the function are the zeros of the numerator. How do you get a y-intercept? Well, the way you always have. Y-intercepts, you just have to plug in x equals 0. Solve for y. Now, what happens if, in the course of doing things, you discover a value that makes the denominator 0? What have you found concerning the graph? You found the vertical asymptote, right? That's the place where you can't have that happen. You can't have 0 in the denominator. So if the denominator is 0, vertical asymptotes so mostly this part should be common sense, and you've done it before. The tricky part of rational functions is really the horizontal asymptotes. Turns out they're not always horizontal. Sometimes they're actually diagonal. It gets complicated. So let's come up with some rules for that. But first, I'm going to write the p and the q as things that look a little bit more like actual polynomials, so we can talk about them a little bit better. Okay, so don't be fooled. Horizontal asymptotes are really just end behavior in disguise. All right? That's really what you're looking for. So, end behavior is going to depend on what happens when you plug in really big numbers, like infinity and negative infinity, right? If I have a function that looks like, well, let's consider 3 kinds of functions. Let me put them up right. Okay, so end behavior of, say, the top one. Say I plug in infinity. Well, you can't quite do that, but say I plug in something really close to infinity, right? Say, okay, 1,000 isn't really close, but it'll work for me. Say I plug in 1,000. 1,000 squared, right? That's 3 zeros, 6 zeros, right? 1 and 6 zeros, plus 1. Do I care about the plus 1? I mean, it's not going to matter. 1,000,001 versus 1,000,000, is that really going to change your end behavior? Probably not, right? So these values out here, they're not really going to matter. And that's why when we talk about these functions and we talk about horizontal asymptotes and end behavior, I don't care what's in these ... areas. I only care about the leading coefficients and the degrees. Okay, so that's the part we're going to focus on here. All right. So I plug in 1,000, I get 1,000,000, whatever. I plug in 1,000, I get 3 zeros times 5, I get 15 zeros. That's an enormous number, right? 1,000,000 over 1 with 15 zeros. That fraction is so small, it's practically 0, right? So the limit as x approaches infinity here is 0. That means we can say if, I'm going to use n for the top and m for the bottom. So if the degree n is less than the degree, the denominator m, then the horizontal asymptote is just what happens if they're the same? So I've got x cubed and x cubed down here. We've determined that these terms really don't matter to me at all. Say, if you don't really feel like you're comfortable with x, we're plugging in huge numbers. Think about it. If I plug in 1,000 here, I've got a billion, right? 4 billion, in fact. And if I plug in 1,000 here, 4 billion plus 2,000, right? It doesn't make a big dent. It's really just the first terms. So on top, I would have 1 billion. On the bottom, I would have 4 billion. And even if I plugged in bigger numbers than 1,000, like a million or infinity, right? I would still have a ratio here because these are really going to cancel out. So my ratio, this is 1, is based on the coefficients. So I can say if n is equal to m, okay, if the degrees are the same, then it's a horizontal asymptote at the place where we have n, a sub n over a sub n. Okay, it's just this fraction right there. I refuse to refilm, but I messed it up, so please fix your notes. These should be y values. Sorry, it's a Saturday. Okay, so I'm all about fixing typos here. These are actually y values, not x values. This is a Saturday, please forgive me. And I changed the x to the third and x squared. So your notes, it should be correct, but on my example, it's not so hot. Let's look at this one. Say I plug in a really big number, like 1,000, like we've been doing. I've got 1,000 cubed, that's 9 zeros, a billion. And I've got 1,000 squared, okay, that's a million. And I cancel those. I had 6 zeros here, 9 zeros here. I cancel them, I get, 1,000. What's happening? I mean, I don't care about this, we've established that, and I don't care about this, so I really have x cubed, let's think about this as y equals x cubed over x squared, and what does that simplify to? Not that this is really legal, but it simplifies to, x. This is highly suspicious. But whatever values I plug in, they're really gonna cancel until I pretty much just have x. What if I had like a 3 here and a 5 here? Well then, when I don't care about those, I reduce this and I get 3 over 5x. Well, what kind of function is this? It's a line, right? And it's not a horizontal line. It's a line with a positive slope of up 3 over 5. This is what's called a slant asymptote. And you get slant asymptotes when the numerator has a higher degree than the denominator. Does that make sense? So if n is greater than m, then slant asymptote